Okay, we are going to go over the workbook page answers in this book right here. This is for blocks 1 and 3. So we are on page 55 of our motion, and this is going to go 55 through 58, which was due today, Wednesday, October 26th. So the very first thing we're going to look at is number 1, something in motion that you cannot see moving. I put in here answers will vary. Some of these things I graded for accuracy, others I graded for completion. This is one I just graded for completion and just looked at it and made sure that it made sense. Anything in here could make sense, something that's moving that you can't see. A lot of you put air because obviously air moves, but you can't see the air moving. You can see the effects of the air blowing something or the wind blowing something, but you cannot see the air itself because air is transparent. You can't see it. Number 2 says an object in motion that is moving in relation to an object that appears to be A, staying in place. Our reference points stay in place. Number 3, when an object changes position over time relative to a reference point, the object is D, moving. Some of you wanted to put accelerating in here. Something can be moving without accelerating. And if it changes position over time relative to a reference point, it could be moving at a constant speed. If it's going a plane flying at a constant speed in a constant direction that's not speeding up or slowing down or changing direction, is showing motion because relative to a reference point it's moving, but it is not accelerating because it's a constant speed at a constant direction. That is no acceleration there. So don't get those two confused. Number 4, for determining motion, the surface of Earth is a common reference point. The ground is a common reference point for motion because compared to us on top, it seems to be still. The Earth, going back up to number 1, you could use that. You can't really see the Earth's motion directly. You can't see the Earth spinning on its axis. You can see evidence for that. Some of you put the planets because maybe they move too slowly. You could graph their motion over time, but when we think about just being able to look without doing anything and seeing motion, those types of things might be up there too. All right, number 6, can a moving object be used if it's a reference point? Technically it can. You could see two objects in motion and tell how they were in motion, 2 planes, 2 cars, the Earth itself. So that could be arguable. This is not. This is one I looked at for completion, just to keep you thinking. It's a higher level thinking question, and some of those things could be argued back and forth. Generally, moving objects do not make good reference points because it's hard to tell. It's hard to tell their motion. Let's look at number 7. The speed of an object depends on the distance traveled and the time. Remember, speed is always dependent upon distance and time. The SI unit for speed is kilometers per hour is acceptable, or meters per second. I also accepted. This is really probably the better one. This was textbook answer in workbook, but meters per second, especially this last part, it has to end in the meter to be the SI unit. Remember, SI stands for Systems International. All right, number 9, why is it useful to calculate average speed? Because many times objects do not travel at constant speeds. That's what I was really looking for in that question, because a lot of times the speed of an object will change second by second, minute by minute, hour by hour, whatever you're comparing that to. So if you look at the average speed, that is a lot more useful than the instantaneous speed or the minute by minute speed. If I was traveling, say I was traveling from here and I had a doctor's appointment in Macon, I might need to know kind of an average speed because I need to know kind of how long it's going to take me to get there. If I travel, an average speed of 50 miles an hour, I need to know how much time I need to allow so I can get to Macon. So that average speed is a lot more useful there than exactly how fast I'm going to go to the stoplight and how fast I'm going to actually be going on the interstate and how fast I'm going to be going on some back roads or how fast I'm going to be going when I get in town. So things that I do not, things often do not travel at constant speed, so they change speed, so the average speed is useful there. All right, let's flip the page, and we're looking at number 10. It says explain how to calculate average speed. So average speed is equal to the total distance divided by the total time. Some of you left off those totals, and I tried to write those in there for you because sometimes you have different parts of trips, like you do the first part of the trip and you stop and you spend the night somewhere, and then you go to the second day, you travel some more, so you'd add those two distances together to get your total distance. And of course, if you're looking at your speed, you wouldn't be necessarily calculating the hours that you stayed in a hotel and spent the night, and you wouldn't calculate those into your average speed if you're looking at speed in that instance. All right, number 11, when a person drives for several hours, how does the distance traveled in 1 hour usually compare with the distance traveled in other hours? It can be different in each hour because it's uncommon on long trips that you would have a constant speed. These speeds would actually vary, would change hour by hour. It's probably going to be pretty close to your average speed overall. It'll be within that range. You're not going to have a time when you're going extremely fast or extremely slow unless you hit different circumstances, which is entirely possible on a long trip. So it will be different for each hour depending on the situation. Traffic, accidents, construction, those types of things can impede your progress. If we look at number 12, it says suppose that on a graph you're showing speed are two lines, and one line represents the speed per hour and the other line represents the average speed. Will both lines be exactly alike and in the same place on the graph? No, these lines showing the speed per hour will not be straight because, again, we just talked about this would be like your speed every hour changing. You've graphed first hour, second hour, third hour, fourth hour, so on and so forth. So depending on what kind of environment that you're in, your speed changes and your slope changes there every hour. Now, the average speed would be a straight line with a constant slope because you're looking at the beginning point and the ending point, and you don't have all of this information. In our notes the other day, we talked about the dog walk, and the dog walked and he sat down or something, and then he took off again. And so when we looked at the average speed, it was just a straight line. The average speed didn't give you that information of where he was running and where he was stopped and whatnot. Same kind of thing here. All right, number 13. Why wouldn't birds end up in the same destination if they're flying exactly the same speed at all times? Because they may not be going in the same direction. Okay, they may be traveling in different directions. And these are my notes here. So I'll write different directions. Some of you put they had different velocities, which is fine as well. Number 14, what is the difference between velocity and speed? Velocity will tell you the rate and the direction, where speed is only the rate. And we've had that and gone over that several times in class. Let's go over to number 15. How would you calculate the resultant velocity of two velocities in the same direction? You add them together. If they go the same direction, they're both considered positive, so you add them together and they take the direction that they're traveling. Number 16, how would you calculate the resultant velocity of two velocities in opposite directions? What direction is the larger velocity? So here's what we talked about in our notes. Some text talks about putting a positive and a negative to it, which is fine. You can do that. To keep it simple for our classes, just the basics, what you're going to do is you're going to subtract the smaller number from the larger number. You're going to find that difference there. And then the direction of the larger velocity will be the motion. So again, in class we said something's going 10 miles per hour north, added to north, and then something was going 5 miles per hour south. And so if you look at those two, they're going in opposite directions, so the difference of those two is 5. It's going to end up going, this object itself, it will end up, its resultant velocity will be in the northern direction by 5 miles per hour or whatever that you're measuring in. Number 17, if your speed is not changed but your direction is changing, are you accelerating? Yes, you are accelerating, because acceleration is a change in speed and or direction. So even if something's the same speed, if it changes direction, you then have acceleration. Number 18, another name for acceleration in which velocity increases is positive acceleration. The two common terms for decrease in velocity is negative acceleration or deceleration. Number 20 says to write the mathematical formula for calculating the average acceleration. So average acceleration is equal to the final speed minus the initial speed divided by the change in time. So V, sometimes this is called V1 and V2, velocity 1, velocity 2. Actually, that's backwards. Excuse me. There we go. Velocity 1 would be your initial speed. Initial meaning beginning speed. Velocity 2 is your final speed. And then remember this little triangle here means delta, which is a change in time. Number 21, a speedometer shows that a cyclist is going 1 meter per second the first second, 2 meters per second the second, and 3 meters per second third second as the cyclist continues straight south. So how do you know that the cyclist is accelerating? So they're telling you that it's accelerating. So how you know this is because the speed is changing. Speed is changing. It's increasing because he's speeding up. He's going this speed and then speeding up to 2, and then he speeds up again to 3. So the speed is changing. It is increasing. So therefore you have acceleration. You actually have positive acceleration. All right, and then the last three. If we look at number 22, it says, how would acceleration be shown on a graph? You would put speed or velocity and time, and that acceleration would show how the speed can be increasing over time. It can show that it would be decreasing over time. That could also be the case because that's acceleration. If it shows a straight line, it could not be acceleration because that means the speed would be constant there. So anytime you have a change in the line on a speed versus time graph, it would show acceleration. If you had a distance versus time graph, which you don't normally show acceleration on, but remember it would be the curved. It would be a curved line like so. So any of those answers would be correct there to show acceleration. Number 23 says a graph shows a roller coaster increasing in velocity for the first 8 seconds as it goes down the hill. Will the graph have an upward slope representing the roller coaster traveling down the hill? Explain your answer. Will it have an upward slope? Yes, it will have an upward slope because we are graphing a change in speed. We don't graph on this one a change in direction. Okay? You're showing an increase in velocity here. So you're showing that increase in speed. It's getting faster and faster and faster. So it does have a positive slope because, again, we're defining speed right here, not direction. And then number 24, as long as something travels in a circle, is it always accelerating? Yes, it's always accelerating because it is constantly changing direction. Anytime you have something going in a circle, an orbit, a path, it goes this way to the left, it goes downward, it goes to the right, it goes upward. So it is constantly changing direction, even though it's going the same speed. It's changing direction, and by definition, acceleration can happen if you speed up, slow down, or change directions. And that's all for out of those 24 questions, pages 55 through 58.